Hello everybody. This is our first video lecture for chapter 18, and I'm going to actually break this up into two video lectures so you don't have one that's just too long. So this is video lecture 18.1 part 1. And we are beginning now chapter 18 in our book Fundamentals of Physics. The title of the chapter is Temperature, Heat, and the First Law of Thermodynamics. And actually, there's a key word in that title, thermodynamics. That is the subfield of physics and engineering that we are talking about for the first two chapters of this semester, chapters 18 and 19, thermodynamics. Let me give you a very big picture view of what this subfield called thermodynamics is about. In the broad sense, thermodynamics is about energy exchanges between a system and whatever its environment is. Okay? That's what thermodynamics is really about in a broad sense. Energy exchanges between a system and its environment. Now, last semester, Physics 110, and yes, we'll be using a lot of ideas, pretty much all of them, from last semester as we need them as we continue to learn more physics this semester. We learned about a concept last semester called work. I know you remember that word. And I will tell you that in a broad sense, I described work as the energy exchange between a system and its environment or surroundings by means of a force. Work is energy exchange between a system and its environment by means of a force. That's going to be important in thermodynamics, since thermodynamics is about energy exchanges. So one way you have an energy exchange is by means of a force, and we call that process work. But now we're also, in these next two chapters, going to introduce another process for exchanging energy between a system and its environment. That process is going to be called, as we will learn, heat. And broadly speaking, heat is the energy exchange between a system and its environment because of a temperature difference between the system and the environment. Now that'll have to be unpacked, and we'll have to explain what we mean by all that, but that will be our second process for exchanging energy between a system and its environment. We'll call it heat. It arises because of a temperature difference between a system and its environment. Okay. Now, one of the concepts that's going to be important in thermodynamics is called pressure. And that's because when we study thermodynamics, it's quite common that we study systems, matter, in the fluid phase, the phase known as a gas. Gases. I think you know intuitively what I mean when I talk about a gas. A gas is a phase of matter. Okay. Oxygen, O2, as you breathe it in the air in the room, is a gas. Also, we will talk from time to time about the phase of matter known as a liquid. And you have an intuitive understanding what I mean when I talk about a liquid. When you talk about either liquids or gases together, you call them fluids. And the fluid is a material that in essence can flow to fit the shape of its container. And so we're going to talk quite a bit about fluids, liquids, and even more so, gases. And when you talk about either a liquid or a gas, the concept of pressure turns out to be very useful. So this little lecture, Lecture 18.1, Part 1, is going to talk about pressure, how we define it, and a little bit about how we measure it. If you want some more information about pressure, by all means, I encourage you to read in your book, which you will get to on Wiley Plus. And specifically, if you want to read about pressure, then I refer you to Chapter 14, Sections 1, 2, and 3. Okay. About fluids, density, we've talked about that concept before, and pressure, fluids at rest, and measuring pressure. I'm going to summarize the key ideas from those sections for you here. And so the first key idea is basically defining the pressure exerted by a fluid upon its container. And what we have drawn here is in red there, we just have a kind of a box that's hollow. And inside that box, we have a gas. For example, maybe oxygen that we have put into this container. And I know you're all aware of the atomic hypothesis of matter, which has been proven by experiment many times over and is taken now to be known fact. We have a bunch of atoms/molecules zipping around inside this box. That's our gas. And the atoms or molecules are bouncing off the walls of the box. And in so doing, when they bounce off the walls of the box, they change their momentum. And when they change their momentum, there's an associated force. Newton tells us that. So these bouncing molecules and atoms, when they bounce off the walls of the box, exert force on the walls of the box. That's going to lead us to what we call pressure. But we don't have to limit ourselves to just the walls of the box. We can imagine looking at any one point in the gas, in its interior, and we can say, what's the pressure at that point in the gas, from the gas? And the way to figure out what that would be is let's do a thought experiment. Let's devise, Vinny is saying hello to everybody, let's devise just a simple little pressure sensor that we could use to measure pressure. And it's drawn down here, and kind of in the bottom part of our picture, right down here below, okay, in an expanded view of the interior of the gas, we've put a little device called a pressure sensor. It consists of a piston, really a cylinder, with a fitted piston inside that can move freely up and down. And on the inner side of the piston, we have a spring with a known spring constant, little k. And on the outside of the piston, it's open to whatever the gas is. And we know intuitively that if we orient this cylinder, let's say up and down, with the piston vertical and the spring vertical, and put it at a certain point in the gas, there will be an inward force on the piston from the gas downward that will compress the spring by some amount until the piston comes to rest and is in equilibrium. Then the downward force of the gas is balanced by the upward force of the spring, and we can use Hooke's law for the spring force. All we got to know is how much the spring has been compressed, and we can from that figure out the downward force of the gas on the piston. And this figure calls that downward force, it may be hard to see in the picture, delta F. So we've oriented the cylinder vertically, and we're measuring the downward force at this point in the gas from the gas. We'll call that delta F. It's acting on that little piston. And that piston has an overall area, delta A. And here comes then the definition of the pressure of the fluid at the specific location where we have this sensor. Symbol for pressure, little p. Definition, take the magnitude of the force from the gas, delta F, and divide it by the area of the piston, delta A, over which that force acts. Delta F over delta A. And so we loosely describe pressure as force per unit area, because we're taking the total force with our little sensor on the top face of our piston, delta F, and dividing that total force by the area, delta A, of that piston face. So force over area on which it acts, force per unit area. Symbol, little p. Yes, we used little p for something else last semester. Do you remember the symbol? Linear momentum. So unfortunately, we're reusing a symbol of the alphabet for a different physical quantity. We have to be clear from the context of what we're talking about, how to interpret that symbol. Here, the symbol little p means pressure. Please note pressure by its definition is a scalar quantity, not a vector. Okay? And yes, there's an intuitive aspect to pressure having a direction because it's associated with force, and force has a direction. So when I orient the pressure sensor vertically, yes, the force on the piston here is downward. But the definition of the pressure is just the magnitude of that force divided by the area. What's the SI unit of pressure? Let's just use the definition. It has to be the unit of force, Newton, over the unit of area. In SI, that's meter squared. So Newton over meter squared is the SI unit of pressure. Now, it is given, by convention, its own name, that unit of Newton over meter squared. It's called the Pascal, PA, named after a French scientist who studied pressure, Pascal. You will come across some other units. Another common unit of pressure is the atmosphere, ATM, and let me just tell you the definition. 1 atmosphere is, by definition, the pressure of Earth's atmosphere down on you when you are at sea level at 0 degrees Celsius. And that has been measured. And 1 atmosphere corresponds to 1.01 times 10 to the 5 power pascals. So that's the conversion factor between atmospheres and pascals. 1 atmosphere is 101,000 pascals. Okay, so that's the concept of pressure. I want to say a little bit more about it. And measuring the pressure in a liquid in static equilibrium as it varies with depth in the liquid. That's the other idea I want to introduce in this lecture. So this picture shows some container open at the top to air and pretty much filled with some kind of liquid. The picture is meant to imply water, but it really could be any liquid. And the pressure of the air right at that top surface of the liquid we'll call P0. That would probably be atmospheric pressure, whatever the local atmospheric pressure is of the air at this location. And if you like, we'll call that surface there, the interface between the air and the liquid, level 1. On a y-axis, which is vertically upward, and we're taking y equals 0 to be at level 1 there, at that surface. Then we've gone to some level 2 below the surface, and it's at a depth h below level 1. And we want to know how to figure out the pressure at that location, level 2. If we put our little pressure sensor at level 2, what would it measure? What would its value be? Okay? See how it's labeled there? P. We'll take the liquid to have some known density, and that density to be uniform. Okay? Remember the symbol? We talked about density a lot last semester. The symbol for density is the Greek lowercase letter rho. That's not a P. That's a rho. And density has unit of kilogram per meter cubed because it is mass per unit volume for a material, and it is an innate property of a material. So this liquid has some known density rho, and it's the same throughout. Okay, so let me just point out some key points about that pressure P at level 2. The pressure P at level 2, at a certain point in the fluid, and this fluid is said to be in static equilibrium, not moving, not accelerating. That pressure depends on the depth of that point, but not on any horizontal dimension of the fluid or its container. To say that another way, it doesn't matter about the side-to-side dimension of the fluid. The pressure here at level 2 is the same whether I'm at that point at level 2, or that point, 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 or that point. All those points are at the same depth. Doesn't matter where you are horizontally, only at what depth are you. That's one key point. And that's actually basically Pascal's principle, which says, based on experiment, that the pressure at any point in a fluid in static equilibrium is the same in all directions. Imagine that little small fluid sensor, pressure sensor. It's very small, and it can be oriented however we want. So if I put it at level 2 and orient it up, then my piston is right here at the top, and I'll be measuring the pressure from the fluid pushing down, and I'll get some pressure. Now just imagine rotating that pressure sensor 90 degrees. Don't move it any, just rotate it 90 degrees sideways. So then I'll be measuring the pressure from the fluid trying to push inward, from my perspective, rightward. But I'll end up using my pressure sensor, I'll get the same pressure as if I had the pressure sensor oriented vertically. But now I've oriented it 90 degrees, rotated it. Same pressure. What if I rotate it 90 degrees again so that the piston is facing down? Then I'll be measuring the upward force from the fluid, but I'll get the same pressure. And if I rotate it 90 degrees again this way, so I'll be measuring the force, the pressure from the force of the liquid pushing to my right. I'll get the same pressure. Doesn't matter what direction you orient your pressure sensor at, you'll get the same pressure at a given location. That's Pascal's principle. So here's the key thing we want to know, and I'm going to show you a little mini derivation of this result, but I want to show you the result now because it's useful. What formula do you use to find the pressure at this level 2 in my picture, the pressure labeled P, which is depth H below level 1, where the pressure is P0. It's this handy formula right here. The pressure at the lower level, level 2, P, is the pressure at the higher level, level 1, which in this picture is P0, plus more, because the pressure at the lower level is greater than the pressure at the upper level. That added part consists of the density of the fluid, rho, times our old friend, little g, gravitational field strength, 9.8 Newton per kilogram, times the depth, h, of level 2 below level 1. Now, do you see physically why the pressure at level 2 is greater than the pressure at level 1, which is higher? Why is the pressure at level 2 greater at the lower level? Can you say why that would be? What you think about that? Did you say that it's because of the weight of the fluid between levels 1 and 2? The fluid has weight. There's a downward force associated with that. That makes the pressure at a lower level greater than the pressure at a level above. Okay? Now I want to show you where that P0 plus rho GH comes from. Be careful, this symbol here is a rho, not a P. So let me show you now that same kind of picture of the container with a liquid, but now we're going to focus on a particular sample or parcel of the liquid. It's outlined with the dashed line there. It's kind of a parallel pipe head shape, okay? And it's just sitting there in the fluid. The fluid is at rest, so all the fluid's at static equilibrium. I'm going to take a plus y axis upward with y equals 0 at the surface, just for specificity. I will say the top level of the liquid is at y1. And the bottom level of the liquid is at coordinate y2. y2 is lower than y1. And both the top surface of this parcel and the bottom surface of this parcel have surface area A. And yes, of course, there are 4 sides this way, in addition to the top and the bottom, and they have some area, but I'm not going to worry about those. All right, we're going to draw a free body diagram for that parcel of water. And that's drawn over to the side where the parcel itself is now represented as a dot. It's a free body diagram. And we're going to draw all the forces acting on this parcel of water. And it turns out that there are 3. There is a downward force on this top surface right up here from the water. It's downward. I'll label it F1. And it's in my free body diagram right there. Now, what about the bottom surface of this parcel? There's a force on that from the fluid. Which way is that? On the bottom parcel. It's got to be up. So we'll call that total force on that bottom parcel F2. And that's represented in the free body diagram there. And I have purposely drawn F2 longer than F1. Why? Because there's one more vertical force acting on this parcel, our old friend F grav. Because that parcel of water, or whatever the liquid is, has some mass. Okay? So there's a gravitational force from that parcel that I'll label F grav. And that's this little arrow right here, which I'm going to label F grav. And those are the 3 forces. Now, if you're wondering about horizontal forces from the fluid on the sides pushing inward, there is. There is a force on what I see as the right side of this parcel pointing in, and there's a force on the left side of the parcel pointing in. But if you think about it a while, you'll discover that those 2 forces are equal and opposite and balance. And there's a force on the front face and the force on the back face, and they're equal and opposite and balance. These are the 3 key forces. 1 up, 2 down. But because the parcel's in static equilibrium, the net force must be 0. So, from Newton's second law, if the net force must be 0, then I can write that the magnitude of F2 must equal the magnitude of F1 plus the magnitude of F grav, right? The 1 upward is balanced by the total of the 2 down when the forces are that simple, pointing in just opposite directions like that. Now from now on, I'm going to use shorthand notation for magnitudes. I'm just going to write the magnitude of F2 like that, F2 vector, and the magnitude of F1 like that. And for the magnitude of F grav, I'm going to use our old friend from last semester. The mass of the fluid, I'll just call it M, of my parcel times the gravitational field strength, little g. Now that M there means the mass of the fluid in that parcel. That's what we're studying here with Newton. Well, the next idea to use is that density, that's a rho, not a p, is the mass of a sample over its volume in a uniform material. And I can rearrange that as mass equals density times volume. And let's substitute that in for the mass of our parcel of fluid. We get F2 equals F1 plus the density of the fluid times the volume of that shaded parcel times little g. But what's the volume of that shaded parcel? Let's write that out next. F2 equals F1 plus rho times. Okay, what is the volume of it? Well, it's a parallelepiped. Okay. So the volume is the area A this way times the height this way. And so I'm going to use A for that area. Now here's how I'm going to denote the height vertically. Y1 minus Y2. And then, of course, don't forget to multiply by little g. Now you have to think about that Y1 minus Y2. Because both Y1 and Y2 are below the origin, so both Y1 and Y2 are negative. But Y2 is more negative than Y1. So when I do Y1 minus Y2, I'm going to get a positive number because all I want is that depth of that sample. Okay? All right. Next, we use that pressure, that's a P, not a rho. Sorry about how those symbols look very similar, is force per unit area. The total force on a surface divided by the area on which it acts. I'm going to use that in both of those force expressions, because all I have to do is rearrange that and say I can think of force as pressure times area. So F2, the force, upward force from the bottom, at the bottom level, will be the pressure at that bottom level, P2, times the area A of that surface of the parcel. Force F1, acting at the top level of the parcel, is the pressure up there at that level, P1, times A. Okay? Plus density times A times Y1 minus Y2 times G. And here's one of the reasons that pressure is useful, because you end up having these factors of area in whatever formula you're working with, and you end up having them in every term, so you can just divide them out. And that cross-sectional area of your parcel doesn't matter. And you get this very useful relationship. The pressure at the lower level of this parcel, P2, is the pressure at the top level, P1, plus more, because the next thing I'm writing is a positive value. The density times what we denote, Y1 minus Y2, which is just the depth of the parcel, times G. Okay? So it just came from Newton and the concepts of density and pressure. Now all I need to do, one more step, is to apply that little formula to the parcel that I had. I just pick an arbitrary parcel here, but go back in the previous picture and in essence think of the parcel as something like that. Doesn't matter what the cross size dimension is, just like that. Then level 1 is at the top, at the interface between the air and the liquid, and level 2 is at depth h, below that interface. And if I apply this little result to that, then what I do back in that formula, right, is I put P1 with the symbol P0, the pressure at that interface, which is the atmospheric pressure of the air. I put Y1 to 0, because level 1's at Y equals 0, the surface. And I put Y2 at negative h, because it's at a depth h below the origin. And when I do that, this formula becomes P2 equals P0 plus rho gh, which is the formula I showed you before, and which is very handy for finding the pressure at a depth h below the higher level. The pressure at the lower level, P2, is the pressure at the higher level, P0, plus more. Rho times g, just times whatever the vertical depth is. Okay? Okay, I'm going to end this video with a little class engagement exercise like we did last semester. And you will write your answer, you will enter your answers on Blackboard. And they are just little conceptual questions. Here we go. The figure shows 4 containers, each with the same olive oil. So the point is, well, it doesn't matter, right, if it's olive oil, that it's the same liquid in all 4. All 4 containers are open to the same atmospheric conditions at the top. First thing, rank the 4 containers. You can see they're labeled here, A, B, C, and D. Rank the 4 containers according to the pressure at depth h, largest to smallest. That's the first part. And then the next part. Suppose we take the top of container D, okay, that's this one, evacuate and seal it off up here at the very top. Evacuate, seal it off. The point being, it's completely sealed off at the top. It's vacuum. Okay? Guess what the pressure at vacuum is? Nothing. Okay? Now rank the 4 containers, all 4 of them, A, B, C, and D, according to the pressure at depth H, largest to smallest. So that's what I want you to do on Blackboard. Conceptual. You don't need to do any calculating. It's conceptual. You just enter your answers there. You'll see where I've set it up on Blackboard like I did last semester. That's all for this video for right now.